v for some time t. So you take an initial condition, flow along this vector field for some time, you reach at another point. So it takes point on the manifold and gives you another point on the manifold. By the theory of differential equations, this guy is a diffeomorphism. It's differentiable. It's differentiable and it has an inverse because I can flow along the reverse of the vector field. So it's a diffeomorphism on M. Okay? So this is the flow map, and I assume that you have seen it in the lecture. We'll have some little bit of repetition here. But like I said, it takes a point on the manifold, takes P, flow along the vector field. So this is the velocity vector V. Here is V at the different point, V at the different point. So this is the integral curve actually for some time. So after some time here, T, this point is, let's add it to a different color. This point is phi for some time T along V from P. So it takes the initial condition and gives you the final point after some time T. The examples that we had in the lecture was V, here's a vector field on Rn, A, just an array, a vector on Rn. Obviously this notation is misused. Why? Because I should write here what? Any suggestion?
TRN.
Very good. The vector field lives in the tangent bundle. Okay? Or if you want to be even more precise, this is a vector field. I don't know what's happening here. Maybe I should get a new battery next time. But the issue is that because this guy is isomorphic to Rn and this is isomorphic to Rn, two people become sloppy as we go. Or I mean, in engineering applications, we don't have this. We don't need this precise language, unfortunately, most of the time. So this is why we become sloppy. But sometimes it really matters. So we need to make this distinction. So how we get the flow map here, as you guys have seen in the lecture, just solve this differential equation. Convert this into a differential equation. So we have x dot, here is an array equals to A. Please solve this differential equation with an initial condition x naught. So you get x of t, that is x naught plus at. Now your flow map phi t along V from any point x is this guy with the initial condition now is x. So this is x plus at. And the other example that we also had in the lecture, V again on Rn is A times x. So now it's not a constant vector field, it varies with the point, it's linear. Again, this is an Rn, or let's say TRn. So the solution, turn this into a differential equation, x dot equals Ax. You guys are experts on this from linear algebra. So you get x of t as e to the at. This is a matrix exponential times x naught. So the flow map phi t v from any x is just a e to the at times x, right? Any question about the flow map?
Is it a special case of integral curve?
So it's a different view. That's a very good question. It's a different view because a curve is a map from the real line to the manifold. So at any given value, the real line, which is time, viewed as time, at any given time gives you a point in the manifold. So this represents the solution of the differential equation as a function of time, fixing the initial condition. So we say integral curve at p. This is a different point of view, which is, now I'm going to fix time actually. I'm going to fix time, say 10 seconds. So in 10 seconds, by flowing along this vector field, by solving these differential equations for just 10 seconds, now the solution, the final solution will be different depending on the initial condition. So this map as taking an initial condition giving you final condition. So it takes a point, gives you a final point. This is a map on the manifold. This is the flow map. Okay? So in general, the solution of the differential equation actually is function of two things. It's function of time and it's function of the initial point, p, right? Yeah, so having this in mind. When we fix t, then it becomes a function on points on the manifold only, function of the manifold. takes point and gives you a point. And this is along a vector field. When you differentiate it with respect to, so this one of its property, when you differentiate it with respect to the first argument, okay? So partial t. So this guy, which we denote by phi tv of p, okay? When we just like to, don't think about t. But if you differentiate this guy with respect to the first argument, you get what? Any expectation about that?
You get the vector field.
You get the vector field, because this is now you need the velocity. So you get the vector field evaluated at what? Obviously evaluated at the flow. Okay? And if you differentiate with respect to the second argument, what do you get? You even think of Rm, don't make it complicated. So this is the solution of the differential equation. Okay? So like e to the at times x naught. If you differentiate with respect to the second argument, the point, or x naught, what do you get? What do you get?
In this case, we get the state transition matrix.
Yeah, here, but in general. So maybe because this is nice and linear. Sometimes it's very highly nonlinear. Say, sometimes it's highly nonlinear, and you differentiate with respect to x naught. So that's okay. What do you get out of that? So phi, this solution is like a vector. Is a vector, right? It's an array, and it depends on x naught. X naught is also an array. So you differentiate an array with respect to an array, you get what?
Jacobian.
You get the Jacobian, right? This is a vector valued function, and I differentiate it with respect to the coordinate. Now this guy, the flow map is function of the point, right? So it's function of n variables in coordinates, and I differentiate with respect to the n variables. You get the Jacobian. It's nothing fancy, but we have a name for this Jacobian in this course.
Tangent map.
That matter, push forward. Okay, just have this in mind. I will not do it here, but have this in mind because sometimes in the proofs we will need to differentiate with respect to the second argument. If you differentiate with respect to the first with respect to time, you get velocity. If you differentiate position with respect to time, you get velocity. So you get the velocity here. But if you differentiate with respect to the second, we get the Jacobian of this guy. Okay? The Jacobian here is easy because it's linear. It's just this matrix. This is the Jacobian, okay, of the flow. Any question about that? Okay, sometimes we will need this notation. Okay, so that's enough with the flow map. So vector fields are right-hand side of differential equations. When we solve them, it's called an integral curve as a function of time. It's called the flow map as a function of the initial condition. And now, because the vector field V at some point P, lives where?
Professor, I have a question.
Sure.
So a little bit up, you converted V to x dot.
V to, yeah.
But what if V is not function in time?
V is not actually indeed a function of time here. This is what I said over there. So we're saying that V is always seen as the right-hand side of the differential equation. Right? To get at least to get the integral curve or the flow map, whenever you have a vector field, you represent it as a differential equation. It represents the right-hand side of the differential equation. You go and solve this differential equation, now you have the flow map or the integral curve. Okay? So V of P, where does this guy live?
Tangent at P.
Yeah, so this guy lives in TPM. So it's what? It's a derivation. So V at P, it takes C infinity function, smooth function on M, and gives you a real number, the directional derivative, correct? So, V at P, if it's acting on F, so it's multiplying by F, this is summation I equals 1 to N. V at P, it has N coordinates, so this is the ith one, partial F, partial little xr, right? This is the directional derivative of F along V, the convective derivative or directional derivative that we talked about last time. And you guys had it in the homework. Any question about that? So now what about v itself not evaluated at a point? It takes C infinity function and gives you what? So at any point, I'll take a function, and at any point I give you a real number. At any point I give you a real number. So for all these points, I'm giving you real numbers for all these points. What does this represent? So it takes a C infinity function and gives you what?
C infinity.
Gives you a function. So obviously, you just one very distinction here is that when you do this computation, you really need to evaluate it at P. So the vector field is already evaluated at P. This guy also had to be evaluated at P to get a real number out of that. So differentiate and substitute by the point. Here, for the vector field, we just differentiate and don't substitute. So you get a function. Okay? So V acting on any f, which is we denoted by V multiplied f, is the same definition, but we don't substitute. Vi partial f partial xi, so we get a function. Is it clear? Do you need an example? I can give you an example. Who needs an example for this distinction? Don't feel shy. Just let me know. I mean, if it's, I don't want to be very boring for you, and I don't want to be very vague. So, if you have, is it clear enough, or you need an example? I can give an example. Don't feel shy.
I want it.
Okay. So let's have this, for example, vector field V is our lovely vector field. Okay.